Here's an example that I think is pretty interesting. Find the total mechanical energy of a hydrogen atom. So mechanical energy is kinetic plus potential. E equals kinetic plus potential. The potential is electric potential. The kinetic energy would be the kinetic energy of the electron plus the kinetic energy of the proton. And the electric potential energy is between the electron and the proton. Okay, so let's figure out each of these things. The kinetic energy of the electron is 1/2 times the mass of the electron times the velocity of the electron squared. An electron has mass 9.11 times 10 to the minus 31 kilograms. It moves with a given speed of 2188 kilometers per second. So 2188 times 10 to the 3 meters per second. That's got to be squared. That gives us a kinetic energy of our electron, 2.18 times 10 to the minus 18 joules. It's a small energy, but an electron has a pretty small mass, so that kind of makes sense. What about our proton? Kinetic energy of the proton is 1/2 times the mass of the proton times the velocity of the proton squared. Well, the proton pretty much stays still. That means the velocity of the proton is about equal to 0. So the kinetic energy of the proton is about equal to 0. Okay, last we have the electric potential energy between the electron and the proton. So for electric potential energy, we've got K times the charge on the electron, which is minus E, times the charge on the proton, which is plus E, divided by the distance between them. And the distance between them we label R. That's given as 52.9 picometers, so that's R. And a picometer is times 10 to the minus 12 meters. Okay, so we've got 8.99 times 10 to the 9 times minus 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19. I'm at a space, so I left out units just for room, divided by 52.9 times 10 to the minus 12 meters. Put all that through the calculator, and what we should get is minus 4.35 times 10 to the minus 18 joules. Okay, let's put all this together. So my total energy then is 2.18 times 10 to the minus 18 joules plus 0 plus negative 4.35 times 10 to the minus 18 joules. That gives us negative 2.17 times 10 to the minus 18 joules. That's kind of an interesting result, that the total mechanical energy is negative. If you wanted to get a really good handle on this, you might have to talk a little bit about energy levels, in a chemistry class, or you might want to get into a little bit of quantum physics. But kind of the gist of it is you would have to do work, you would have to put energy into this system to bust apart the hydrogen atom. So I think that's pretty interesting. Okay, let's do a conservation of energy problem. A proton is fired from far away. You might want to ask yourself, what does that mean by distance? At a 1 millimeter diameter glass sphere. So here's our proton, here's our glass sphere. The proton has been fired or projected towards it with some initial velocity. And our glass sphere has been charged to 100 nanocoulombs. What initial speed does the proton have to just get to the glass? And we know the mass of the proton and the charge of the electron. So we're going to be using conservation of energy, which says that the final energy is equal to the initial energy plus work done by non-conservative forces. There's no friction or anything like that. So we know the work done by our non-conservative forces is going to be 0. Okay, let's start by fleshing out what we know about the initial situation. So initially, the proton is moving towards the glass sphere. They're separated by some distance, R initial. Now here's a good place to point out that R stands for the center-to-center distance. Because they are far away, we can say that our R initial is about equal to infinity, because infinity is far away. Okay, let's write down what we would get for our energy. So our initial mechanical energy is the initial kinetic energy plus the initial potential electric energy. The initial kinetic is the proton plus the glass. And let's see what we would have to fill in for each of these. The kinetic energy of the proton is a half times the mass of the proton times the initial velocity of the proton squared. The kinetic energy of the glass is going to be 0 because our glass is still, it's not moving. And our initial electric potential energy is K times the Q of the proton times the Q of the glass divided by our initial. Now this guy is about equal to 0 because our initial is about equal to infinity. Okay, so here's our initial energy. Let's move on to the final case when the proton just reaches the surface of the glass. And you might ask yourself, what is that telling us that it just reaches? Okay, let's do final next. So final, the distance between the centers we'll call RF. And our final energy is equal to K final plus UE final. K final means K final of the proton plus K final of the glass plus UE final, which is the final potential energy between them. So for our proton, it just reaches. If it just reaches, it means it stops as it gets there. So V final of the proton is equal to 0. Our glass is still not moving. So V final of the glass is equal to 0. So the final kinetic energy of our proton is 0, a half times m times 0 squared. K final of the glass is 0, a half times m times 0 squared is 0. And we're left with just the final potential energy, which is K times the charge of the proton times the charge of the glass divided by RF. Now our RF is the distance between the center of the proton and the center of the glass. A proton is very small, and the glass has a radius of 0.5 millimeters. So the diameter of our glass is 1 millimeter. So then the radius is 0.5 millimeters. Okay, I think we're all set now to put our conservation of energy together. We know our initial energy, we know our final energy. We can put it in our conservation of energy and solve for the initial. Let's write down our expression for conservation of energy again. E final is E initial plus work done by non-conservative forces. That's 0 if we don't have anything like friction or air resistance. So our E final was K times Q of the proton times Q of the glass divided by our final equals our E initial, which was 1/2 times the mass of the proton times V initial of the proton squared. So V initial of the proton squared is going to be K times Q of the proton times Q of the glass divided by RF. Going to have to multiply that by 2 and divide by the mass of the proton. To get our velocity then, we'll have to take the square root of both sides. And let's fill in our numbers. 2 times 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Charge of a proton, 1.6 times 10 to the minus 19 coulombs. Charge of the glass, that was given as 100 nanocoulombs. Divided by the mass of the proton, 1.67 times 10 to the minus 27 kilograms. And that's also divided by our RF, which was the radius of the glass sphere, 0.5 millimeters. Notice we're putting everything in SI units. Put all that through your calculator, and what you should get for your answer is 1.86 times 10 to the 7 meters per second. That is a very large speed. It doesn't exceed c, so we're okay, but we should recognize that it is pretty fast.
Here's a question I'll leave to you as a homework example. I won't do a video, but I will post the solutions. So we have an interaction between elementary particles which causes an electron and a positron. So that means it has the same mass as an electron, but a positive charge. So that's a positron, that's an electron. They're shot out back to back with equal speeds. What is the minimum that this value of speed must be if they're 100 femtometers apart? A femtometer you might not be familiar with. That's 10 to the minus 15 meters. In order for the two particles to escape each other, for them to escape, what that means is that the final velocity is equal to 0. So I'll leave that to you to try. You should apply conservation of energy here and see if you can figure it out. So here's a slightly different kind of example. We have 3 protons and they're arranged on an equilateral triangle and they're fixed in place. So I've got protons 1, 2, and 3. First part of the question is, what is the potential energy of this system of charges? This is different because now we have 3 charges instead of 2. If we only had 2 charges, say 1 and 2, we'd be able to do that. It would be K times Q1 times Q2 divided by the distance between them. So there's an energy between charges 1 and 2. But we don't just have charges 1 and 2, we also have charge 3. So there's a potential energy between 1 and 3 and a potential energy between 2 and 3. To get the total potential energy, you have to add up all the combinations. So the energy between these two, plus the energy between these two, plus the energy between these two. So whenever we have multiple charges, the total electric potential energy is equal to the sum of every combination. So in terms of this problem, the total potential energy, UE, is the energy of 1, 2, plus the energy of 1, 3, plus the energy of 2, 3. Now this is nice and symmetric, which is going to make our calculations easy. Let's calculate the energy between 1 and 2 first. So the electric potential energy between charges 1 and 2 is K times Q1 times Q2 divided by R12. R12 is the distance between charges 1 and 2. For notation, I'm just going to call that R. My charge 1 is a proton, my charge 2 is a proton. So Q1 equals positive fundamental charge, Q2 equals positive fundamental charge. Okay, so that gives me K times E divided by R. So 8.99 times 10 to the 9 newtons meters squared over coulombs squared times E squared 1.6 times 10 to the minus 19 coulombs squared divided by R, which is 59. A femtometer is 10 to the minus 15 meters. I think I have just enough room to squeeze in my answer. That's equal to 3.90 times 10 to the minus 15 joules. So that's the energy between charges 1 and 2. What about between 2 and 3? So UE 3 is equal to K times charge 2 times charge 3 divided by R23. Well, R23 is 59 femtometers. That's the same as R. Q2 and Q3, they're the same charges because they're all protons, so Q3 is also E. So for the energy between charges 2 and 3, I've got K times E squared over R. That's the same as the energy between 1 and 2. And likewise for the energy between 1 and 3. Okay, so that's where the symmetry makes this problem nice and easy to solve. So my total potential energy is the 3 interactions added up. They all have the same value, so I can take what I found for the energy between 1 and 2 and just multiply that by 3. And that gives me a total potential energy of that entire system of charges of 1.17 times 10 to the minus 14 joules. that's the total potential energy of these 3 protons when they're fixed in place on this triangle. Okay, part B of the question says we take proton number 2 and we let it go. What is the maximum speed it could possibly reach? So let's think about the motion. If we let charge 2 go, it's repelled by charges 1 and 3. It's going to move upwards. So we know it's going to move away because it's repelled. If it gets to a maximum speed, it's going to have a maximum kinetic energy. When you have maximum kinetic energy, you have minimum potential energy. That tells us we're going to have the maximum speed when this proton is really far away. So let's think about conservation of energy and see if we can find that speed. We're going to use conservation of energy to solve our problem, which says that our final energy is equal to our initial energy plus work done by non-conservative forces. We don't have any friction or air resistance, so that work done is equal to 0. So let's think about our initial case and our final case. Our initial case is at the beginning when we've got our 3 charges arranged on our triangle. The initial energy is equal to the initial kinetic plus the initial potential. We already know the initial potential because we all figured that out. And what we know about these charges is that they're initially fixed in place. So they're not moving, which means the initial velocity is equal to 0, which means that the initial kinetic energy is equal to 0. So our total initial energy is 1.17 times 10 to the minus 14 joules. Okay, initial is taken care of. What about final? Final is when our proton number 2, our top proton, has moved very far away. It's moving with some speed that we'd like to find, and we know that it's far away. We know that it's far away because we want a minimum potential energy because that gives us a maximum kinetic energy. So for our final distance between charge 2 and 1 and between charge 2 and 3, our final distance, let's just label it big because we're far away. And a number that's big is about infinity. Okay, what are we going to say for our final energy? So our final energy is our final kinetic plus our final potential. Okay, let's be really careful with each of these terms and let's think about them each in turn. So K final equals K final of 1 plus K final of 2 plus K final of 3. Now, K final of 1 is fixed in place, so that's 0 because that one hasn't been released. Number 3 is also fixed in place, so that guy is 0. But charge number 2, that one is moving because it was released. Okay, so our final kinetic energy then is 1/2 times the mass of charge 2, mass of a proton, times the velocity of proton number 2 squared. So there's our K final. Our UE final is still the potential energy of each set of charges. So it's UE of 1, 2 final plus UE of 1, 3 final plus UE of 2, 3 final. Okay, let's think about each of these things in turn. So UE of 1, 2 is K times charge 1 times charge 2, that's a proton times a proton, divided by the distance between 1 and 2. The distance between 1 and 2 is big, so U over a big number is about equal to 0. Okay, this is true also for the potential energy between 2 and 3. Okay, and that's because they're far apart. Okay, what's left? The potential energy between 1 and 3. 1 and 3 are not far apart. So the potential energy between 1 and 3 is K times the charge of 1 times the charge of 2 divided by the distance between 1 and 2. So that's our 59 femtometers. We found that value on the previous slide. That was 3.90 times 10 to the minus 15 joules. Okay, now we have an expression for our final energy. E final is K final, which was 1/2 times m times Vf squared, plus our UE final, which is 0 plus 0 plus 3.9 times 10 to the minus 15. Okay, let's put it all together with our conservation of energy. Final energy equals initial energy. So as we finish up, we'll put what we know about the initial and final energy into our conservation of energy equation. E final is a half times m times Vf squared plus 3.90 times 10 to the minus 15. And that's equal to our E initial 1.17 times 10 to the minus 14 joules. So 1 half times m times Vf squared is 1.17 times 10 to the minus 14. Take away 3.90 times 10 to the minus 15 joules. We'll divide both sides by a half times m, where m is the mass of a proton. And then we'll take the square root to get our final velocity. And when we do that in the calculator, we should get 3.06 times 10 to the 6 meters per second. So as that moves far away, it actually gets to go pretty fast.